Okay, hello everyone. Thanks for the introduction. Today I'm going to talk about multi-party non-interactive key exchange from ring key homomorphic weak PRFs. This is a joint work with Hart Montgomery and Shikhar Patranabish. As you all know, key exchange is a fundamental cryptographic primitive which has been widely used in many cryptographic applications and protocols. Essentially, key exchange provides a mechanism to exchange keys over an insecure communication channel. Usually, key exchange protocols are categorized based on two properties or two features. One is the number of parties that are involved in the protocol, and one is the number of back and forth exchange messages between parties that are involved in the protocol. In particular, if each party broadcasts a single message, we would call such a protocol a non-interactive key exchange protocol, or NIKE. Otherwise, the protocol would be called an interactive protocol. So in this talk, I'll be focusing on non-interactive protocols, or NIKEs, so there won't be anything related to interactive protocols. Now, let's take a look at some prior works and see how much progress has been made over the past few decades regarding non-interactive key exchange. So an initial progress in this direction was the original Diffie-Hellman key exchange protocol. You know, there are two parties, Alice and Bob. Each party samples a random element from ZQ. Let's call them A and B, and then they send G to the A and G to the B to each other, where G is some generator in the group. And then the final key is computed as G to the AB, or by applying some key derivation function on top of it. So this protocol can be simply viewed as a two-party key exchange protocol. A couple of decades after the invention of this protocol, Joe showed the construction of three-party NIKE from bilinear maps, which was later then followed up by a generalized construction of NIKE for n parties, given a multilinear map with degree n-1. There are also constructions of multi-party NIKE from strong non-algebraic cryptographic assumptions, such as indistinguishability obfuscation or functional encryption. However, despite much progress, a question that remained unanswered so far is that, can we construct multi-party NIKE from simple and generic cryptographic primitives with algebraic structure? And by simple and generic, I mean cryptographic primitives in the symmetric key world, such as pseudo-random generators or pseudo-random functions. So what we are looking for in this work is to focus on a particular well-known cryptographic primitive, augment it with algebraic structure so that we can get a multi-party NIKE. So we make progress on this question by showing that a ring key homomorphic weak PRF implies a multi-party NIKE. So our result can be seen as an extension of prior works, which showed that key homomorphic weak PRF is sufficient to construct two-party NIKE. In other words, if you view a weak pseudo-random function as a base and simple primitive, if you augment it with group homomorphism, you can get two-party NIKE. If you strengthen it further with ring homomorphism, we can construct a multi-party non-interactive exchange out of it. So one immediate question that comes into mind is, what about key homomorphic PRFs where the homomorphism is with respect to field homomorphism? In this work, we rule out the existence of field key homomorphic weak PRFs. And so given our results, we get a somewhat complete picture of implications of weak pseudo-random functions with algebraic structure. So in this talk, I'll be focusing on our main result, which is constructing multi-party NIKE from a ring key homomorphic weak PRF. So concretely, here's an outline of the rest of my talk. So first, I'll recall some definitions and cryptographic primitives that we'll need for the construction. So I'll start with the definition of a weak pseudo-random function, and then we'll see definitions of key homomorphic weak PRF and ring key homomorphic weak PRF. Once we became familiar with definitions, I'll show a construction of three-party NIKE from a ring key homomorphic weak PRF, followed by some proof ideas. And then I'll describe a generalized construction that works for any number of parties. Finally, I'll conclude with some open questions and future directions. So let's start with the definitions. So we say that a function family is a weak PRF If no attacker can distinguish between samples of the form xi and the evaluations of fk on xi's from a random tuple where xi's are generated randomly. So as you can see in the definition, this is simply a weakened version of a pseudo-random function or a plain pseudo-random function where the attacker gets to see evaluations on randomly chosen inputs as opposed to adversarially chosen ones. It's long been known that once you have a weak PRF, you can construct basically any cryptographic application in the symmetric key world, such as symmetric key encryption or message authentication code. But it's impossible to get any kind of public key encryption functionality, at least in a black box way, out of a weak pseudo-random function. However, things change when we augment this simple primitive with group homomorphism. So here we have the definition of a key homomorphic weak PRF. We say that a weak pseudo-random function is a key homomorphic weak PRF if the key space and the output space are groups with efficiently computable group operations. And for any input x, there is a group homomorphism from the key space to the output space. So this can be simply viewed as like for any input x, and for any two keys k and k prime, if you evaluate f on sum of k and k prime and x, it's going to be equal to sum of individual evaluations. Although I won't be focusing on this particular primitive in this talk, it is worth mentioning that you can construct a simple key homomorphic weak PRF out of the DDH assumption where the evaluation is just an exponentiation. Now, let's see the definition of a ring key homomorphic weak PRF, which is a cryptographic primitive that we introduce in this work. So we say that a weak PRF is a ring key homomorphic weak PRF if the key space and the output space are rings with efficiently computable ring operations. And for any two keys and any input x, if you evaluate f on sum of k and k prime and x, it's going to be equal to sum of individual evaluations. And a similar thing also holds with respect to multiplication. So a natural question that comes to mind at this point is that why we are choosing weak PRF as the base primitive and augment it with ring homomorphism. Indeed, in the paper, we introduce other ring-based notions, such as ring input homomorphic weak PRF or ring homomorphic synthesizers, and we show that even these primitives are sufficient to construct multi-party NIKE. But I'm going to explain our construction only in terms of a ring key homomorphic weak PRF or RKHW PRF. Now, let's see the construction. So I'm going to show you a construction of multi-party NIKE based on an RKHW PRF without even evaluating RKHW PRF on any input. So one surprising aspect of the construction is that even though the construction is based on an RKHW PRF, we are not going to evaluate the function on any input. Let's see the construction. So suppose that we have an RKHW PRF. I'm going to assume that we have two uniformly sampled square matrices in the public parameter where n is a sufficiently large integer that is polynomial in the security parameter. So we have three parties who want to do a key exchange: Alice, Bob, and Charlie. Each party is going to sample a uniform matrix from the output space of the RKHW PRF. So Alice samples A, Bob samples B, Charlie samples C. Next, Alice is going to compute her public key or her public message by computing A, Y0, where A is Alice's own secret randomness, and Y0 is the matrix that is included in the public parameter, and Alice is going to publish PA next. Bob is going to publish two matrices, Y0B and BY1, where B is Bob's own secret randomness, and Y0 and Y1 are the public matrices included in the public parameter. And finally, Charlie is going to compute PC, which is equal to Y1C. So again, C is Charlie's secret randomness, and Y1 is included in the public parameter. Now let's see how each party can compute the final key. So Alice can compute the final key by computing PA times PB0 and PC, where PB0 and PC are the matrices that Alice got from Bob and Charlie. Similarly, Bob is going to compute PA, B, PC, where PA and PC are the matrices that Bob got from Alice and Charlie. And a similar thing is going to hold with respect to Charlie. Now, let's quickly check why this key exchange protocol satisfies correctness. So if you look at this slide, you can essentially see that each party is going to compute the same value A, Y0, B, Y1, C. For instance, if we look at how Alice computed her final key and replace PB0 with Y0B and PC with Y1C, it's immediate to see that this expression here is equal to A, Y0, B, Y1C. And the same thing also holds with respect to Bob and Charlie. So it's immediate to see that this key exchange protocol at least satisfies correctness. Now let's consider the security of the protocol. So the proof of the protocol basically boils down to the fact that given the public parameters and the public matrices are that computed by all parties, the final key is computationally indistinguishable from random. So the proof is going to be done in 3 steps. First, I'm going to show the pseudo-randomness of matrix products with large enough dimensions over the output ring of any ring key homomorphic weak PRF. This is basically the crucial part of the proof. And then from here, we are going to go to a downsides version of the protocol where Alice and Charlie sample a vector instead of a matrix to do the key exchange protocol. And finally, we can finish the argument by a simple information theoretic argument over modules. So let's start with the pseudo-randomness of matrix products over the output ring. So suppose that we have an RKHW PRF, and suppose that n is a sufficiently large integer. Assume that we sample a vector of inputs and a vector of keys for some integer m and n. Now consider the following matrix M, which I'm going to form as follows. So I'm going to use the same key in each column and the same input in each row. Now, if I sample a binary vector of dimension n, I can say that this product ms here is going to be equal to f of k star xi's by relying on the key homomorphism of f. So this basically means that ms can be simply viewed as evaluations of f on k star xi's, where k star is basically a subset sum over the key vector using the binary vector s. So at this point, I can rely on the leftover hash lemma to say that k star itself is distributed uniformly, and hence m star is computationally indistinguishable from random because this is simply weak PRF evaluations on a fresh key. So this means that given m, ms is computationally indistinguishable from random. Now here's a more interesting part of the proof. Because the matrix M itself is weak PRF evaluations, we can switch M to a completely uniform matrix Y, and then say that given a uniformly chosen matrix Y from the output space of the RKHW PRF, Ys is computationally indistinguishable from random. And as you can see, this holds for any number of rows. So the only requirement here is that n is large enough so that I can apply the leftover hash lemma. Now, so far we saw that for a binary vector S and a uniform matrix from the output space of an RKHW PRF, Ys is pseudo-random. We can rely on a simple statistical argument to say that it's also OK if S is uniformly sampled from the output space instead of being a binary vector. And furthermore, we can rely on a simple hybrid argument to say that the computational indistinguishability holds even if F is a matrix instead of being a vector. So given that any ring key homomorphic weak PRF should satisfy this property, it is immediate to see that there is no field key homomorphic weak PRF because matrix products can be easily distinguished from random given any field just by solving a linear equation. Okay, so remember that we wanted to prove this indistinguishability to establish the security of the key exchange. Now, we can rely on the pseudo-randomness of matrix products to switch a y0 to a random matrix TA and y1c to a random matrix tc. We can rely on the pseudo-randomness of matrix products once again to say that it's just enough to prove this statistical indistinguishability on the bottom, which basically says that given 4 public vectors, y0, y1, ta, and tc, and the product of y0 and y1 with some matrix, some secret matrix P, the term TABTC is statistically indistinguishable from random. So the security of the whole protocol basically boils down to this statement here. So this statistical indistinguishability is very easy to prove over sufficiently large fields, but it requires a much more involved argument over rings. So we are basically trying to prove that given an adversary both of the pairs y0 and y0b, along with y1, by1, the adversary cannot learn enough information about b to distinguish the final term from random. So the proof of this statement over rings is similar to the proof of leftover hash lemma, but it's more tailored towards ideals of a ring, and I'm going to eliminate the remaining part of the proof. So let me quickly describe the generalized construction. So there's nothing magical with number 3. You can actually generalize the construction to work for an arbitrary number of parties. So we are going to assume that y1 through yn minus 1 are basically n minus 1 randomly generated matrices from the output space of Arkesh WPRF. The first party is going to sample a secret matrix S1 and publish S1Y1. For each intermediate party, there are going to be 2 matrices. One is yi minus 1 si, and the other one is siyi. And the final party is basically going to compute yn minus 1 sn, where sn is the last party's secret. Similar to the 3-party case, each party can compute the expression as the final key, where we are going to embed these public matrices in between secret matrices. For instance, the first party can compute the final key as the product of S1 times P20 through Pn minus 10 times Pn, where these P matrices are the public matrices that the first party got from all other parties. So I'm going to conclude my talk with a few open questions. So perhaps the most interesting question is to see whether there is any candidate construction of Arkesh WPRF from mathematical assumptions, or if you want to be on the pessimistic side, can we rule out the existence of Arkesh WPRFs? And this is not an easy question because this would require an algorithm to solve linear equations over any ring. The third question is to construct multi-party Nike from weaker primitives, such as ring homomorphic pseudo-random generators. And the final one is to get a symmetric multi-party Nike protocol from an Arkesh WPRF, because as you saw in the construction, our protocol is asymmetric in the sense that each party is doing something different. Thanks for your attention. Yeah, that's true. This can be seen as analog of the non-interactive key exchange that you can get from learning with rounding assumption, where your A matrix is going to be embedded in the public parameter. But it's true that unlike the Diffie-Hellman key exchange protocol, where you can, just use an arbitrary generator, this is going to require some setup.
Are there any known Nike protocols that have no setup like that?
I mean, it depends on your definition of setup, but if you are okay with saying that, okay, we can use any generator, then maybe the Diffie-Hellman protocol itself can be viewed as a version of the protocol that you want.
What is the relationship between multilinear maps and this PRF? Do you know if there's like by implication or
Good
implications?
question. So you can define a bounded version of this primitive where there is a bound on the number of multiplications that you do. So you can weaken the definition in a few ways to actually get what's called like a bounded RKHWPRF, which in turn you can instantiate it based on multilinear maps. Yes. But then for that bounded version, you won't be able to instantiate it for any number of parties. So the number of parties that you can have in your protocol is going to depend on the degree of the multilinear map that you are starting with. On the reverse direction, you mean? I guess it's going to be different because in multilinear map case, the exponent basically defines a field, the exponent space. But here you have a ring, so I guess the main problem is basically going to boil down to the fact that here you have a non-commutative ring, and you want to get something that has a field in it. So I don't think that's going to be like likely, unless you again weaken the definition in some ways. Okay.
Yeah, thanks for the talk. So in the multilinear map, you need just one round, like everyone just broadcasts their public key, like share the public key. Here you need like n rounds.
No, it's not n rounds. Like I explain it in a way that like each party is doing different.
So each
but, like,
ith party has to wait for the message from the I-1 party, and so on?
No, you don't need to wait. Like there are like 2 matrices published per each party, but it's not the case that the party number I needs to wait for party I-1. So it's a non-interactive protocol.
Okay, I see, thanks.
Okay, welcome. This talk is about joint work with my colleagues Sebastian and David from Technical University of Darmstadt and Kamit from Bar-Ilan University. My name is Benjamin Schlosser, and I will going to talk about the paper Putting the Online Face on a Diet. So in MPC, we have a scenario where we have multiple parties and they can communicate with each other. The parties may have some private inputs, they interact with each other, and then they obtain their outputs. And the goal of the entire interaction is to compute some specific function on their inputs to get the outputs. And in a setting where we have multiple parties, it may also happen that some parties are corrupted and behave maliciously. And in MPC, we consider different types of adversaries. On the one hand, there is the semi-honest setting where the corrupted parties follow exactly the protocol specification, but they try to learn additional information from the interaction with the other parties. On the other hand, we have the malicious setting. Here, the adversary can act arbitrarily. And it's clear to see that security against malicious adversaries provide a much higher level of security, but at the same time, we need to incorporate more expensive prevention mechanisms. So we get more efficient protocols in the semi-honest setting. So as a middle ground, Aumann and Lindell introduced the covert security setting. Here, the adversary is also allowed to act arbitrarily, but it is only willing to cheat if the probability that its cheating will be detected is below some parameter. And the reason behind this security model is that if the parties value their reputation and they fear of getting caught, then they refrain from cheating at all. And this provides a higher level of security than semi-honest security, but and at the same time, we can also construct protocols that are more efficient than in a malicious setting. So I will tell you something about one specific technique, the so-called cut and choose technique, which was used by all prior known protocols for covert security. And this technique starts with a semi-honest protocol, and instead of executing it only a single time, we execute it multiple times. And then after the execution, we randomly decide on one instances and check all the other instances. And if the check turns out to be valid, so every party behaved honestly during the checked instances, then we take the remaining instances as the output. But if we detect that a party, at least one party, behaved maliciously in at least one instances, then we directly abort. And the adversary, if he wants to cheat in the unchecked instance, then he has to guess this instance, like the index of this instance, already in the execution phase. And the probability for this is 1 over t, so we have a detection probability of 1 minus 1 over t. And we call this detection probability also the deterrence factor, which is usually denoted by this epsilon. You might now wonder, how can we actually check protocol execution? And on a high level, we need to reveal all the inputs that the parties use for this execution so that the parties can recompute the behavior of the other parties. But at the same time, we still want to keep every secret information secret. So there is one approach that is used by many covert protocols, and this is the offline-online approach. Here we split the entire protocol execution in 2 phases. We have an offline phase where the parties only use random values as inputs. The output of this offline phase is so-called correlated randomness. And then in the online phase, the parties use their actual inputs together with the correlated randomness to compute the final outputs. And it's called offline-online because in the offline phase, the parties only do not use their private inputs, so we can recompute this, or we can pre-compute this already before knowing the actual inputs. And at the same time, using this correlated randomness, we can speed up the online phase. So we get a very fast online phase when the actual inputs are present. And here you can see that in the offline phase, we only use random inputs. So it's no problem to reveal these random values. So we can easily apply the cut and choose. And in the online phase, we just take a maliciously secure protocol. And it was shown by Damgard, Orlandi, and Simkin in 2020 that when combining a covert offline phase with a maliciously secure online phase, then the entire protocol is covertly secure. And so far, the belief was that since the online phase is anyway kind of fast, there is no real benefit in making this also covertly secure. And this is exactly the belief we challenge in our work, and we explore what are the opportunities of reducing the security of the online phase to covert security. So for this, we first introduced a new paradigm to achieve covert security. So we have seen the cut and choose technique, and now we have a new technique which gives us covert security from short message authentication codes. Then we apply this paradigm to the online phase of the TinyUT protocol, and we also show that we get some improvements in the communication complexity of the covert variant of TinyUT protocol. And finally, we show that we can make this composition, so we can combine a covert offline phase and a covert online phase without weakening the overall security. And we formally stated with our deterrence replacement theorem. So let's start with our new paradigm for covert security. So we have seen we can move from semi-honest security to covert using the cut and choose technique. So basically amplifying semi-honest security. Now we have the idea to move from malicious security to covert, so by weakening the security. And we do this by reducing the statistical security parameter. In the malicious setting, the cheating probability, or the probability that an adversary successfully cheats, is a negligible function in this statistical security parameter. For concrete instantiation, this parameter is typically set to 40, 60, or 80. And we show that we can get covert security by using a lower value for this statistical security parameter. So let's look at a concrete instantiation of this new idea. Here we use message authentication codes. This is a tool that is used by some MPC protocols to ensure the correctness of the computation. In particular, here we consider one-time max for authenticated bits, and these are linearly homomorphic max, so we can compute on these values. So when using such a tool, the scenario is typically like the following. We have two parties. The left party knows the authenticated bit together with the MAC on this bit. And the right party knows a local key, which is unique for this bit X, and a global key, which is the same over all authenticated bits, like authenticated towards the other party. And these keys and the MAC are T-bit strings. And now, as I said, this is a linearly homomorphic MAC, so the parties can compute on these, on the MAC and the bit. And after the computation, the left party can send the bit together with the MAC to the right party, which recomputes the MAC and checks if this is the correct MAC. And only if this is the correct MAC, then it accepts this bit. And now, if the left party is maliciously and wants to flip its bit, then it has to add here, it has to XOR the global key. And since this is a T-bit string, the probability to guessing this bit, this global key correctly is 1 over 2 to the power of t. So we get a detection probability of 1 minus 1 over 2 to the t. And this is how we get covert security from short message authentication codes. And now we apply this new paradigm to the TinyOT protocol. So this TinyOT protocol is a two-party protocol for computing arbitrary Boolean circuits. And we chose this as a demonstration protocol because it's a well-known protocol, and we also state in our paper that we can extend our that we can apply our paradigm to extension of the TinyOT protocol. So let's give you an overview on this TinyOT protocol. So this is also in the offline-online approach. Again, the parties use random values as input to the offline phase, and now the correlated randomness is in the form of authenticated bits, which we have seen before, and authenticated triples. And this means that we basically have an A and B equals C, where A, B, and C are secret shared between the parties. So that we have A1 XOR A2 and B1 XOR B2 equals C1 XOR C2. And all of these shares are authenticated. And then the parties use these correlated randomness together with the input to compute the outputs. And finally, they perform a MAC check on the MACs that are revealed during the execution, and only if the MACs are valid, then they output their final outputs. Okay, so how can we transform this into a covert variant of the TinyOT protocol? So first, for the offline phase, we just apply the cut and choose paradigm. As we have seen, there are only random values, so we can easily apply this. Then we take the correlated randomness that is produced in the instance that is not checked in our online phase, and here we use an online phase with shorter MACs. And we show in our paper that that both transformations are indeed covert protocols. And now one main insight is that by reducing the security of the online phase, we not really get benefits in the online phase, but we reduce the requirements to the offline phase. And by this, we can improve the efficiency of the online phase. So to quantify this effect, we calculated the communication complexity of the offline phase. So for our cut and choose parameter t, we set the MAC length to be the logarithm of t. That's just because we want to have an adherence factor in the online phase is the same as the deterrence factor of the offline phase. And then we calculated the communication complexity for different deterrence factors. And then for these 40-bit max, which is required for maliciously secure online phase, and for mbit max. And we can see for these three examples here, we get an improvement of at least 35%. Okay, so we have seen we can get some benefit of reducing the online phase. And there's one question, what are the costs of weakening the security in the online phase in terms of security? I already spoiled that it's basically for free, but let me give you an intuition why. So for modeling offline-online protocols, we followed the approach that was used in prior works in this area, and we used the hybrid model. So this means the parties, we describe the online protocol in a setting where the parties have access to some ideal functionality, denoted by this F offline. And this functionality replaces the offline functionality, the offline phase. So the parties get the correlated randomness from this functionality. And since we're in the covert setting, the parties also can cheat in these functionalities by sending a special cheat symbol. And the functionality then decides with probability epsilon here in the superscript if the cheating is detected or not. So the adversary now may either cheat in the offline phase by sending this special cheat symbol or during the interaction of the online protocol. And when analyzing the security of the online protocol, we need to consider both opportunities. So for analyzing the security and also for calculating the deterrence factor. So this is how we model it. Now we state our deterrence replacement theorem. And here we start in a hybrid model where the detection probability of the offline phase is actually 1. So there is no successful cheating at all. And let's consider this online protocol is covertly secure with the deterrence factor of epsilon on. Then we move to another hybrid model where we replace the deterrence factor of the online phase with some smaller value, epsilon star. And our deterrence replacement theorem now states that the online protocol is still secure in this model, and we can calculate a new deterrence factor as the minimum of the previous deterrence factor and the new deterrence factor of the offline phase. So since we replace the deterrence factor, we call it the deterrence replacement theorem. Okay, let me clearly state what are the benefits of this theorem. So we start in a hybrid model. As I said, there is no successful cheating at all. So this simplifies the security analysis and also the calculation of the deterrence factor. And then we can replace the deterrence factor of the offline phase with a smaller value. And we can directly derive the security and also the calculation of the new deterrence factor. And coming back to the question, what are the costs of weakening the security of the online phase? And here the answer is it comes for free if we set the deterrence factor of the online phase greater or equal to the deterrence factor of the offline phase. Because since we compute here the minimum anyway, so if we set it just greater or equal to the deterrence factor of the offline phase, then the overall security is the same. Okay, so to summarize, we have seen this new paradigm to get covert security. Can also think about this as a tweakable security from shorter max. And we have shown that we can speed up the offline phase by using a covert online phase without actually reducing the security. And some open question. So we have shown that we can use this paradigm for Boolean, so for protocols that work over Boolean circuits. An interesting question is, does this also work for protocols for arithmetic circuits? For example, the Speeds family. And another direction would be to extend the paradigm to get covert zero-knowledge proofs by weakening the soundness parameter. So if you have any answer to this question, I'm happy to hear next year a talk of you. So thank you very much.
How does the performance of your protocol compare to running an existing maliciously secure protocol, but with a lower statistical security parameter?
I mean, so basically, our online phase is basically, I mean, we need to slightly modify it to get really covert security, but it's basically a malicious protocol with just a smaller statistical security parameter. We have to add some commitments to really get covert security, so there is some constants overhead, which we had to add, but besides this, it's basically a malicious phase with a lower statistical security parameter.
Following up with the question, for what deterrence factor will the maliciously secure protocol outperform the covert secure protocol, or like will it always be better, like the covert protocol?
Yeah, good question. So since we have only a constant overhead in our covert protocol, it really depends on the function you calculate. Like how's the depth of the circuit that you're computing. But definitely if you like set the deterrence factor so that you have 40-bit max, then for sure a 40-bit maliciously secure phase is faster, because then you also have this constant overhead node.
Right. Also, you rely on cut and choose, where you need to, like if your deterrence factor is like 99% or something, then you have to repeat like 100, have like 100 instant, like for the cut and choose, 100 copies and only one of them will be opened. In that case, like the covert protocol will be slower than the malicious protocol.
Okay, so you're talking about the offline phase. If we
Offline
take a
phase,
yeah. Yeah, that's a good question. I think this also depends on the function, because depending on the function, you have to compute more or less of the pre-computed data. But it would be really interesting to see some, like, having some concrete function that you evaluate and then think about it. Yeah, but I cannot give a clear answer to this.
Thank you. Yeah.
Over there was a question.
Is there a fundamental difficulty to apply your techniques to speeds? Because you list this as an open question, but the way you presented it, it was so clear that it should just apply to speeds, but maybe there's a difficulty that you
Yeah, we think so, because in speeds, the MAC value is basically a field element. And this would mean we need to reduce the size of the field, but since we are computing over arithmetic circuits, we also want to have some, like a field that is usable for the computation. So for Boolean circuits, you just can shorten the length of the binary strings.
Anyone else? Going once? Twice?
Okay, thank you very much.